Here's a question that sounds embarrassingly simple. What's the biggest star we know of? And yet, if you actually try to answer it properly, you'll find yourself falling down one of the most fascinating rabbit holes in modern astronomy. It turns out the answer is genuinely contested, like actively debated right now in peer-reviewed papers by professional astronomers. And the more you dig, the more fascinating and kind of wonderfully weird the whole story gets. So today we're going to answer that question. But the answer isn't a single star. It's more like a trial, with three very serious suspects and some truly bizarre twists. Before we meet our three candidates, let's quickly set the scene. And that's because understanding why this is so hard actually makes the whole thing way more interesting. The stars we're talking about are called red supergiants, or at the most extreme end, red hypergiants. Think of them as the elderly, bloated versions of massive stars. Stars that started their lives maybe 20 or 30 times the mass of the sun, burned through their fuel at an insane rate, and then puffed up to truly monstrous sizes before exploding as supernovae. To give you a sense of scale, our sun has a radius of about 700,000 kilometers. That already sounds huge, but the stars we're about to discuss have radii in the range of 1,500 to 2,000 solar radii. And here's the key problem. Measuring the size of a star is genuinely hard. We can't lay a ruler across it. We infer the radius indirectly, from the star's distance, its brightness, and its temperature, using a relationship called the Stephenson-Boltzmann law, which is very solid physics. But if any one of those inputs is uncertain, especially the distance, your radius estimate can be wildly off. And as we'll see, distance is exactly where things get messy. Also, many of these stars are shrouded in thick clouds of gas and dust that they themselves have ejected. So you're trying to measure the star through a fog it created, which, is not ideal. Here's a thing worth knowing. Wikipedia's own list of the largest known stars, which is the reference most people land on, includes a disclaimer right at the top that all sizes have inaccuracies and may be disputed, that the list is a work in progress, and that parameters are prone to change. That's not Wikipedia being sloppy. That's an honest reflection of where the science actually is. Let's start with WOH G64, a star I actually made an entire dedicated video about because its story is that rich. I'll keep it brief here, but if you want the full picture, I'll link that video right here and also in the description. The short version, WOH G64 sits in the Large Magellanic Cloud, a satellite galaxy of our Milky Way, about 160,000 light-years away. For decades, it was considered either the largest known star or the largest with a well-measured radius, at around 1,540 solar radii. In 2024, it became the first star outside our galaxy ever to be directly imaged in close-up, a historic moment in astronomy. But that same year, a separate study suggested it may have quietly shrunk, transitioning from a red supergiant to a smaller, hotter phase called a yellow hypergiant. More recent work in 2026 then challenged that interpretation, arguing the star is still a red supergiant and the weird behavior was caused by a companion star passing close by. So as of right now, even the status of this star is genuinely unresolved. It's either approximately 1,540 solar radii or roughly half that. Active science, happening in real time. But the reason WOH G64 is interesting for this video is also something subtler. It lives in the Large Magellanic Cloud, which is a different galaxy with different chemical composition than the Milky Way. And that actually matters, because the theoretical ceiling for how large a star can get may not be identical in every galaxy. The physics of stellar evolution shifts slightly with metallicity. The abundance of elements heavier than hydrogen and helium. So WOH G64 isn't just competing for the size title, It's doing so under slightly different rules, which makes direct comparison with our Milky Way candidates genuinely complicated. Now let's meet the star that most sources will tell you holds the current record, Stephenson 218, also known as ST218, or Stephenson 2 DFK1. It sits roughly 19,000 light-years away from us in the constellation Scutum, near an open cluster of red supergiants called Stephenson 2. And its estimated radius, derived from a 2012 study using radio telescope observations and dust modeling, is a staggering 2,150 solar radii. That is genuinely extraordinary. Even at the speed of light, traveling around its equator would take almost 9 hours. Around the Sun, that same trip takes 14.5 seconds. And so it sounds open and shut, right? Stephenson 218 wins. Case closed. And, well, not quite. Because there are a few things about this measurement that make astronomers nervous. First, the distance is deeply uncertain. The 2012 estimate assumed ST218 is at roughly the same distance as the Stephenson 2 cluster, about 5.8 kiloparsecs, or about 19,000 light-years. But here's the thing. It's not even confirmed to actually be a member of that cluster. Its position is outlying. Its proper motion is slightly atypical. The uncertainty in its distance has been noted to exceed 50%. And since we calculate radius from distance, luminosity, and temperature, if the distance is off by 50%, the radius calculation can shift dramatically. Second, the star is surrounded by an extremely thick dust envelope, which absorbs and re-emits radiation. That's because it has one of the highest known mass loss rates of any red supergiant. Modeling how much light gets blocked by all that dust is tricky, and different models give you different answers. Third, and this is perhaps the most philosophically fascinating issue, the estimated size of 2,150 solar radii exceeds what current stellar physics predicts should be possible. There's a theoretical ceiling for how large a cool supergiant can get, sometimes described through what's called the Humphreys-Davidson limit or the Hayashi limit, essentially a boundary beyond which the star becomes so internally unstable that it can't hold itself together anymore. That limit sits at roughly 1,500 solar radii. Stephenson 218's estimated size blows right past it. Now, that doesn't automatically mean the measurement is wrong. It might mean the theoretical models need updating. That's happened before. But it's a red flag that makes careful scientists want more data before crowning ST218 definitively. And so, let's bring in our third suspect, Westerlund 126, also written as W26. This star lives inside one of the most extraordinary environments in our galaxy, the Westerlund 1 superstar cluster, about 15,000 light-years away in the constellation Ara. Westerlund 1 is remarkable in its own right. It contains at least 6 yellow hypergiants, 4 red supergiants, 24 Wolf-Rayet stars, and is thought to be one of the most massive young star clusters in the Milky Way. And in the middle of all this stellar chaos sits Westerlund 126, a red supergiant or red hypergiant with some of the most wildly varying size estimates you'll encounter in astronomy. Depending on which study you look at, estimates range from a relatively modest 1,165 solar radii, a 2019 thesis using infrared photometry, all the way up to a jaw-dropping 2,550 solar radii from an earlier spectral energy distribution fit. That's an enormous spread. And that's because measuring stars in a dense, dusty cluster environment is extremely challenging. Nearby stars, interstellar dust lanes, and model assumptions all create noise. The most commonly cited estimates place W26 at around 1,530 to 1,580 solar radii, which would make it comparable in size to a conservative estimate of WOH G64. But here's what makes W26 uniquely interesting scientifically. In 2013, astronomers discovered it is surrounded by a glowing cloud of ionized hydrogen, a nebula. And that's because it was apparently the first ionized nebula ever discovered around a red supergiant through optical emission lines. That nebula suggests W26 has had violent mass ejection episodes. It's behaving like a star right on the edge of stability, possibly approaching the end of its red supergiant phase. Here's what I think is actually the most fascinating takeaway from all of this. And that's because the competition for biggest star isn't really a competition between stars. It's a competition between measurement methods, between different models, different telescopes, different assumptions about dust geometry and temperature profiles and cluster membership. Think about what astronomers are actually doing here. These stars are thousands or tens of thousands of light years away. They're completely invisible to the naked eye. Most of them can only be observed in infrared wavelengths because visible light is absorbed by the dust they're wrapped in. The stars themselves are so large and diffuse that their outer layers kind of blur into the surrounding ejected material. There's no sharp edge you can point to and say, this is where the star ends. So when we say a star has a radius of 2,150 solar radii, what we really mean is, given our best current model of this star's distance, temperature, and luminosity, this is the radius that makes the physics equations balance. It's a model output, not a tape measure. And that's not a criticism of the science. That is the science. You might reasonably ask, who cares which star is technically the biggest? And honestly, fair question. But the reason astronomers care intensely about accurately characterizing these extreme stars is that they tell us something important about how stellar evolution works at the limits of what physics allows. Stars like these, right on the theoretical boundary of stability, are our best natural laboratories for understanding the Humphreys-Davidson limit, mass loss mechanisms, and what happens to the most massive stars in the final thousands of years before they explode. Before we look forward, I want to zoom out for a second, because everything we've discussed so far, 1,500, 1,700, 2,150 solar radii, is really just the red supergiant neighborhood, and the universe has some genuinely wilder things going on. There's a category of stars that can temporarily blow past all of these numbers. During what's called an LBV eruption, that stands for luminous blue variable, or during certain violent stellar mergers known as luminous red novae, a star can expand catastrophically fast and reach sizes of thousands or even tens of thousands of solar radii within just a few months. A star like Eta Carinae or V838 Monocerotis, for a brief window of time, becomes physically larger than Stephenson 218 at its most inflated. Then it shrinks back. So technically, the largest star at any given moment might not be a red supergiant at all. It might be something in the middle of exploding. That's not a loophole. It's a genuine astrophysical point about what we mean by size. And then there are the theoretical objects, quasi-stars, hypothetical structures from the very early universe where a massive black hole forms inside a giant stellar envelope, could theoretically have reached radii of up to 14,000 solar radii or 10 billion kilometers. Our entire three-way competition for 2,000 solar radii would look like a rounding error. Then there are candidate dark stars detected in JWST data, with estimated radii possibly surpassing 10,000 solar radii, though these are extremely speculative and actively debated. These aren't stars we're likely to encounter in a ranking anytime soon, but they serve as a useful reminder. The universe almost certainly has extremes we haven't found yet, and possibly extremes our current physics doesn't fully predict. And so where does this leave us? Honestly, in a genuinely exciting place. The ESO's Extremely Large Telescope, the ELT, currently under construction in Chile and expected to see first light in the late 2020s, we'll have the resolving power to directly image even more of these extreme stars in the Milky Way and beyond. Combined with upcoming VLTI improvements and next-generation infrared surveys, we should start getting much more precise distance measurements and direct radius determinations that don't rely as heavily on atmospheric models. My honest prediction? The biggest star rankings are going to keep shifting. Stars that currently look enormous may turn out to be closer or cooler than assumed. Stars we've overlooked because they're buried in dust may turn out to be the true giants. And there may be stars out there, still uncatalogued in dusty corners of our galaxy, that dwarf everything we've talked about today. So the crown? It stays contested, and that's exactly how it should be. If you found this interesting, drop a comment with which candidate you think will ultimately hold the record, and let me know what other extreme stars you'd like covered.